Hello friends, so today we are going to solve questions from heat and thermodynamics, and these questions are from the year 2005. We are having two questions, 2006 also two questions, 2007 also two questions, and from 2009 we are having three questions. So in total we are going to solve 9 questions. The first question, it was asked in the year 2005, and it states that a metal of mass 1 kg at constant atmospheric pressure and at initial temperature of 20 degrees centigrade is given a heat of 20,000 joules. Find the following. So based on this we are going to find out three things: change in temperature, work done, and change in internal energy. And various things like specific heat, coefficient of the cubical expansion, density as well as atmospheric pressure are given to us. So first of all, in part A, we are more or less, these questions are all the three parts A, B and C are directly related with the formula itself. So first one is the change in temperature, and that is at constant atmospheric pressure. So we start with part A. So you can say that the heat capacity at constant pressure heat capacity at constant pressure, suppose that is given as Q, then this Q will be equal to over M multiplied by C multiplied by delta T. And we can rearrange it. We can say that our delta T will be equal to Q upon mass into our specific heat, that is our C. And Q is given to us as 20,000, and mass is also given to us as 1 kg, and C is given to us as specific heat is of 400. So here this 0 goes by 0 and we are left with 200, and this goes by our 50. So we get change in temperature is our 50 degree centigrade. Now we come to our work done, and for work done, that is our part B. And we know that our work done at constant pressure suppose that is our W will equal to P multiplied by delta V, where delta V is our change in volume. So we can find out the change in volume, and that will be, for that we are going to require our initial volume. So we can say our initial volume and let us call this as Vi will be equal to our basic formula, mass multiplied by density, and mass is 1 kg, density is given to us as 9000. Therefore we get our volume will be equal to 1.11 into 10 is power minus 4 meter cube, and we can say that the change in volume, because we are given the coefficient of cubical expansion is given to us, so we can easily find out the change in volume based on the initial volume. So we can say change in volume that is our delta V will be equal to initial volume multiplied by the cubical volumetric expansion and change in temperature, that is our delta T. And we simply substitute the value, we get this as delta V will be equal to 1 upon 9000 multiplied by, and the ratio is given to us as 9 into 10 to the power minus 5, and change in temperature is our 50 degrees centigrade. Therefore we get our delta V will be coming as our 5 into 10 to the power minus 7 meter cube. So therefore work done, W will be equal to our P delta V. P pressure is our atmospheric pressure, which is 1 into 10 to the power 5. Change in volume is 5 into 10 to the power minus 7, and this comes as our 0.05 joules. Now we can find out our part C, which is change in internal energy, and for that we are going to use first law of thermodynamics. First law of thermodynamics, which gives us that the change in internal energy will be equal to our Q minus W, and we know both the values, so we substitute that, we get this as delta of U, and this is about 20,000 minus 0.05, and that will approximately should be 20,000, but exact value will be 1.999.95 joules. Next question. It was also asked in the year 2005, and it states that a spherical body of area A and emissivity 0.6 is kept inside a perfectly black body. Energy radiated per second by the body at a temperature T is. So this is directly based on the formula, which is our Stefan Boltzmann law. So we can say Stefan Boltzmann law, it says that our energy radiated per second which is our P, is equal to our emissivity, Boltzmann constant, and area, and fourth of power of our temperature. And in the question it is given that the body is inside a perfect black body. Okay, and so it means that the emissivity of the spherical body is not affected. Okay, so we can use this formula directed. So we can say from here, since the body is inside a perfectly black body, it does not affect the emissivity of the spherical body. Itself. So therefore this Stefan's Boltzmann law can be directly used. So we are only given the value of emissivity, therefore we can write that our power will be equal to 0.6 Boltzmann constant, area, and T raised to power 4. Okay, so this will be our, so this will be 0.6, and option number A is correct. A is correct. Next question. It was asked in the year 2006 and states that a black body of a temperature T is inside a chamber of temperature T naught. Now the enclosed chamber is slightly open to the sun such that temperature of the black body is T and the chamber T naught remains constant. So based on this we are having these 4 options, and so this question is divided into 2 parts. First, when it is inside the chamber and the chamber is closed. In the second part, it is slightly opened, and then we can say we have to find out how the black body, first A and B are almost same. It is only difference of the more radiation and less radiation, and C and D is also same. It talks about the emitting more energy and emitting equal energy. So first of all, let's try to understand the black body radiation. And black body radiation is our nothing but Stefan's Boltzmann law. So we can say our absorption of black body radiation you can say that our black body absorbs all incident radiation and emits radiation based on its temperature. So, and it is governed by Stefan's Boltzmann law. Stefan Boltzmann's law, and which gives us that the power emitted will be equal to Boltzmann's constant A and temperature raised to power 4. Okay. And this power emitted, we can also call this as a energy emitted per unit time in watts, and T is the absolute temperature. And in case of absorption by a black body, we have to remember that it is going to absorb entire radiation irrespective of the wavelength or source. Okay, so it means the power absorbed only depends upon the incident of intensity of incident radiation. So we can say that power absorbed depends on intensity of incident radiation. Incident radiation. Okay. So it means it does not depend upon the source, or we can say wavelength. Okay. So it is not dependent upon the source as well as wavelength. And from here we can also, we can say, discuss the concept of thermal equilibrium. And so our thermal equilibrium, so under this condition the body should be having a constant temperature, which basically means that energy absorbed should be equal to energy radiated. So we can say for a body to maintain a constant temperature, we can say that our energy absorbed, so we can say power absorbed should be equal to power emitted. Okay. And we can say also that in this particular case, if the, because it is said to be a closed chamber at a temperature of T naught. Okay. And so from here we can say that the chamber walls, if assumed to be a black body at a temperature of T naught, is going to emit the radiation by same, but only difference will be here temperature will be T naught. Therefore we can say that the chamber walls assumed to be a black body, therefore black body at temperature T naught, at temperature T0. So from here we can write that the emitted radiation so we can denote this as emitted radiation power of the chamber will be equal to Boltzmann constant, area, and its temperature, that is T0. And so it means this amount of the power will be absorbed by the black body from the chamber walls in a closed system. Okay. So it means if the emitted radiation from the chamber is sigma A T04, so the same amount of the power will be absorbed by the black body, which is also inside the chamber. Okay. So let us consider our two scenarios. First is initial, when the chamber is closed, and second will be our when it is partially opened. So we can say our initial scenario, which basically is closed chamber. And it is given that in the closed chamber, black body temperature is T, black body temperature is given as T, and the chamber walls temperature is given as T0. Chamber walls temperature is given as T0. Therefore, we can write that the power absorbed by the black body from the chamber walls, say power absorbed by the black body from chamber walls, and let us denote it as a P absorbed from initial, and that will be equal to our rho A T0 whole raised to power 4, and the black body is going to emit the radiation based on its own temperature. That temperature is our T. Therefore, we can say that black body emits power based on its own temperature. Let us call this as P emit, and this P emit will be our Boltzmann constant, area, and our T4. And so we can say it is also mentioned that the temperature is constant. Therefore, we can write that since black body temperature T is constant, so it means it is having a thermal equilibrium. So there is thermal equilibrium, which basically means that the P absorbed initial should be equal to P emitted, and we substitute, we get this as sigma A T naught whole raised to power 4 is equal to sigma A T raised to power 4. Okay. And from here we can write that our T naught is equal to T. So it means initially when the system is closed or chamber is closed initially, the temperature of the black body and the chamber is same for the equilibrium to hold. Okay. So let us consider a new scenario. And this new scenario is chamber is opened slightly. Chamber is open to sun. So it means as soon as the chamber is open to the sun, there will be some additional radiation enters the chamber. So from here we can say that additional radiation enters the chamber. And we can you can say model that the sun radiation can be modeled as that of a black body which is at a very high temperature. So we can also say that the black body which is inside the chamber is now going to get the radiation from two sources. One will be from the chamber walls and other one will be from our sun. Therefore we can say the black body now absorbs first radiation from chamber walls, radiation from chamber walls, and the chamber wall temperature is still at T naught. There is no change in the temperature. Okay. It is given that the chamber is still at T naught. So radiation from the chamber walls at temperature T naught, and that will be equal to our Boltzmann constant, area, and T naught raised to power 4. And secondly, we can say additional radiation from the sun. Additional radiation from sun. And let us call this as P sun. So it means total power absorbed by the black body. So we can say total power absorbed by black body, we can call this as P absorbed, but this is our nu will be equal to our Boltzmann constant, area T04 plus power because of the sun. And we know that power of the sun will be obviously greater than 0, and say that power because of the sun will be greater than 0. Therefore, our power absorbed nu will be greater than power absorbed initially. Okay. So if we check our option number A will be a correct one because it absorbs more power. So obviously option B is automatically incorrect. So from here we can say option A is correct. A is correct. And let's check our option C. And option C and D we can just make let's discuss option D. If option D is correct, then obviously option C will be our incorrect. Okay. 1 second. Okay, first because it is okay, there is a possibility that both C and D can be correct if I'm not wrong. Okay, so let us check option C, black body emit. Okay, it is talking about emission, and it is D is talking about the comparator. Okay, let's discuss option C. And option C, we know that we just derived that our P emit initial will be equal to, or our Boltzmann constant, A T raised to power 4. Okay, but we know that our T is equal to T naught, so this will be equal to our sigma A and T naught raised to power 4. And when our chamber is opened, we know that our P absorbed nu is equal to sigma A T naught 4 plus power because of the sun. Okay. And for the temperature to be same, because the temperature is same, so we can say that for temperature to remain T, the emission must be equal to absorption. The emission must be equal to new absorption. Therefore, we can further write it that our P emit nu will be equal to our P absorption nu, which is given as A T04 plus P, and this is our sun. But we know that our P naught sun is greater than 0. So we know that our P sun is greater than 0. Therefore, we can say that our P emit nu will be greater than our sigma A T raised to power 4. And 1 second, I think I missed something. Yeah, this is correct. Sorry, my mistake. I thought that the option is written as equal. Okay, but is correct one. It is written as greater than. Okay, therefore we can say that the black body emit more energy. So option C is also correct. Option C is correct. Now we come to the option D, which says that black body emit energy equal to energy absorbed by it. So we have our option D, and we already know that our this is already calculated everything, so we can say our P emit will be equal to Boltzmann constant E area T raised to power 4, and our P absorbed nu will be equal to our A T04 plus P of our sun. And for temperature to remain constant, these should be equal. So we can say our P observed nu is equal to our P emit. And this is true for constant temperature. To maintain constant temperature. Therefore, our option D is also correct. So we have A, C and D. Option D is correct. Next question. It was asked in the year 2006 and it states that in an insulated vessel 0.05 kg steam at 373 Kelvin and 0.05 kg of ice at 253 Kelvin are mixed. Find the final temperature of mixture in Kelvin. And we are given latent heat of fusion, latent heat of vaporization, specific heat of ice and specific heat of water is given to us. Okay. So in this case we know that our ice is at 253 Kelvin and its temperature is going to rise up till 373 Kelvin. So you can say that heating the ice from 253 to 373 Kelvin. Okay. And melting of ice to water we know is going to take place at 0 degree centigrade. Melting of ice to water at 0 degree centigrade. And we can also say that the resulting water from 0 degree centigrade to a final temperature of T degree centigrade. So you can say heating the resulting water from 0 degree centigrade to the final temperature of T. Okay. And obviously this is to be done with the help of steam. So steam is going to condense from 0 degree centigrade to a water at from 100 degree centigrade to water at 100 degree centigrade. So we can say condensing steam at 100 degree centigrade to water at 100 degree centigrade, and then this condensed water will be cooled from 100 degree centigrade to a final temperature of T degree centigrade. So you can say cooling the water cooling the water, and this water is from condensed steam, from condensed steam from 100 degrees centigrade to the final temperature T. So in this case, the water will be formed by two processes. First will be because of the melting of the ice, and second will be formed because of the condensation of the ice. Okay, and the final temperature in both the cases, from the condensation as well as from the ice, will be our same. That is, here we have set that our T. And we basically are going to use energy conservation and find the value of T. Okay. So we start with heat gained by the ice. And this heat gained by the ice will be consisting of two steps. First will be from 253 to 273 Kelvin. So we can say that our heating ice from 253 Kelvin to 273 Kelvin, or we can say minus 20 degrees centigrade to 0 degree centigrade, and that is directly based on the formula. So we can say our, let us suppose we call this as heat Q1 will be equal to our mass of the ice, specific heat of the ice, and the temperature difference. We can call this ice, or we can also call it initial. Okay, and we substitute it. We are given this as 0.45. Specific heat is given to us as 2100, and delta T will be our 273 minus 253, that is about 20. And from here we get this will be our 18900 joules. And next will be our melting ice to water at 0 degree centigrade. Melting ice to water at 0 degree centigrade, which will be our latent heat. Okay, so we can call this as Q2 will be equal to M of I and L fusion. So we have this as our, it is given to us as 80 calorie. Okay, both joules and is given, so it doesn't matter. So we can say this as our 450 grams multiplied by 336. This will be our 151 and 200 joules. And if we require in our calorie, we can also calculate it as 455 multiplied by 80, and that will be equal to our 36,000 calorie. Okay, so these are interchangeable, it doesn't matter that much. Now we are going to heat the water from 0 degree centigrade to a final temperature T. Okay. So we can say that our heating water from 0 degree centigrade to a temperature T, and therefore we can write this as Q3 will be equal to m of I specific heat of water, and we have difference in temperature, and we substitute the values. M of I is our 0.5 kg and this is our 4200. Difference in temperature is T minus 0, so we get Q3 will be equal to 1890 T, and this in joules. And we can also write in calorie. We can write this as 450 T calories. Now total heat gained by the ice, assuming all the ice melts. So you can see from here that total heat gained by ice, and we assume that all ice melts. So we get this as Q ice total will be equal to Q1 plus Q2 plus Q3, and that will be equal to over 170,100 plus 1890 T, and this is in joules, and we can also write in our calories. So this will be our 40500 plus 450 T, and this is our calorie. Okay. And let's find out now heat lost by the steam. Heat lost by the steam. Okay, so it will be two step, from 100 degree steam condensation to 100 degree water, and from 100 degree to final temperature T. So we can say our first part is our condensing steam at 100 degree centigrade to water which is also at 100 degree centigrade, and we can write this as, let us suppose, our Q4 will be equal to our mass multiplied by latent heat of vaporization. So this comes as our 50 multiplied by 2268. This will be coming as 113400 joules, or we can write this as in terms of calories 27,000 calories. Now second part is our from 100 degree centigrade to T degree centigrade. Cooling of water from 100 degree centigrade to T degree centigrade. So let us call this as our Q5. So we can say our Q5 will be equal to MS, and we have specific heat of water and our temperature difference. So we get this as our 0.5 kg multiplied by 4200 and temperature difference will be our 100 minus T. And this can be written as our 210 100 minus T joules, and in calorie we can write this as our 50 100 minus T in calorie. So therefore heat lost by the steam. You can say this is equal to our Q steam total will be equal to Q4 plus Q5, and we substitute it, we get this as our Q4 is our 11,3400 plus, and we open it, we will be getting this as 21,000 minus 210T, which will be equal to 13,400 minus 210T in joules, or in calories we can write this as our 32,000 minus 50T, and this is in calorie. Now we can use that our energy conservation. We have that our Q steam total will be equal to Q ice total. Therefore we just calculate in the joules or calorie, it doesn't matter. So let's try for joules. So this we get 13,400 minus 210T is equal to 170,100 plus 1890T, and let me put the answer directly. This T will be approximately coming as minus 17 degree centigrade. So which basically means that this temperature is well below 0 degree centigrade. So it means the ice doesn't melt. Okay, we can say from here, sorry, not all the ice melts. We can say means not all the ice melts. And if the ice doesn't melt, therefore we can say that some of the ice is still unmelted. Therefore we can say that some of the ice is unmelted. Therefore its final temperature will be our 0 degree centigrade, or we can say it will be our 273 Kelvin. Okay. Yes. Yes, only this was asked for. Next question. It was asked in the year 2007, and it states that a fixed thermally conducting cylinder has a radius r and height L0. The cylinder is open at its bottom and has a small hole at its top. A piston of mass m is held at a distance L from the top surface as shown in the figure. The atmospheric pressure is P0. So based on this we are having two questions. Okay, let us call this as part A and part B. In part A, it states that the piston is now pulled slowly and held at a distance 2L from the top. The pressure in the cylinder between the top and the piston will be then. Okay. And part B, while the piston is at a distance of 2L from the top, the hole at the top is sealed. The piston is then released to a position where it can stay in equilibrium. In this condition, the distance of the piston from the top is. So basic figure is given to us. Total length of the cylinder is over L0, and initially the piston is at a length at a distance L from the top, and the total width of this piston is given as 2R. Okay. So let us solve for part A. And in the initial setup, the piston is at a distance L from the top. Okay. So let us call this as initial state. And in this initial state, we have given that piston is at a distance L from the top. And therefore, we can say that the volume of the gas between the cylinder and the top. Therefore, we can say initial volume, rather, much more easy to remember. So we can initial volume, let us call this as V initial, will be equal to pi r square multiplied by L. Okay. And okay, now it is also given that the cylinder is open at the bottom, and so it is open at the bottom. So here it will be having a pressure of P0, and there is a small hole on the top also. Okay, and at this particular position, we can say that the pressure inside the gas, which is between top and piston, must balance the forces acting on it. Okay. Or in the simpler terms, we can say that the small hole at the top, because of this, the gas inside can be approximately at the same pressure that is our P0, okay, so that it remains balanced. Okay, we can just make a rough conclusion from this part. Okay. So let's find out what will be the forces on the piston, then we can just discuss it more in detail. So you can say that our forces on the piston. Okay. And first of all, you can say the piston is at equilibrium or stationary, so all the forces acting on the piston should be in the balanced state. So first is our atmospheric pressure from the below. So first is our atmospheric pressure from below. Okay. And that is our P naught, and this will be a pi r square, and the direction will be upward. Okay. Now second is our pressure of the gas inside. Pressure of the gas inside. Okay. And that pressure will be our P, and this comes as r square, and it will be in downward direction. And next will be weight of the piston. Weight of piston, which is our mg, and it will be also in downward direction. So at equilibrium, upward forces, downward forces, they are going to balance each other. So you can say for equilibrium, we can write upward force is our P naught pi r square, downward force is P pi r square plus mg, and from here we can say that our P is equal to P naught minus mg upon pi r square. But we have to remember that there is a small hole at the top of the piston, of the cylinder, sorry. So it means the gas inside the cylinder is in communication with the atmosphere. Okay. So from here we can also say that this is a typical open system with a small hole. Okay. Then the pressure inside would be P naught. Okay. So now let us consider how the hole is going to play an important part here. So we can say that our role of small hole. And when there is small hole, it is also said that the piston moves slowly. So you can say that piston moves slowly, therefore the air can enter or exit through the hole. Maintaining the pressure inside the cylinder inside the cylinder at atmospheric pressure. At atmospheric pressure P naught. Okay. And we can also say that because of this our slow movement allows the gas to remain in equilibrium with the atmosphere. Okay, this is the same meaning. And the thermally conducting cylinder ensure that it is at a constant temperature. Okay, so basically it is moving slowly such that the pressure inside the cylinder is at atmospheric pressure, and because of this slow movement of the cylinder, this entire process is our isothermal process. So we can also say that thermally conducting cylinder ensures constant temperature. Constant temperature, or we can say isothermal process. Isothermal process. Now let us come to our new state when the piston is at 2L. We have a new state, piston at 2L. So therefore new volume, or we can say our final volume, that is our V final, will be equal to pi r square multiplied by 2L. And the only difference is no doubt the process is isothermal, but we cannot use the ideal gas law which states that PV is equal to constant directly. The reason is that because of the this open hole, this allows the exchange of the gas, atmospheric pressure or gas, along with we can also, there is a mass exchange keeping the pressure at a constant P naught. So we can say that PV is equal to constant, doesn't apply directly, because the open hole allows mass exchange. Mass exchange. Therefore, we can say that once again in the new state the forces will be also balanced. Thus we can say that our force balance will be giving us P naught pi r square is equal to our P pi r square plus mg. And if our P is equal to P naught, therefore we can say that our P naught pi r square is equal to P naught pi r square plus mg. Now if we solve this equation, it gives us that the mg will be equal to 0. Okay. And so it means our this is only possible if we have our mg is negligible, or we can say the piston is held externally. Okay. And because there is a term used in the question, it says that it is held at a distance L. Okay. So this is quite a open statement, that is, it is being held. So held means there is some kind of force which is trying to hold it at this position. Therefore we can say that the pressure inside the cylinder will be nothing but our P naught, because if we ignore this term held, then our mg will be equal to 0. So which is quite, you can say, not possible at all, unless until we have a negligible mass, okay, of the piston. Therefore we can say that the pressure inside will be our P naught. Because it is quite open statement, it is said that it is being held. And now we come to the part B, and now the hole is being closed. So part B. So in this part B, we can discuss it before closing the hole and after closing the hole. So let us say our initial state. And this initial state is basically means at a distance of 2L, or we can also call it as a before sealing. And we can write that the volume, that is our V, will be equal to pi r square multiplied by 2L. And after sealing, that is our, we can say after sealing, and releasing. After sealing and releasing, and let us assume that the new equilibrium position is at a distance x from the top. After sealing and releasing, the piston is at new equilibrium position new equilibrium position at a distance x from the top. From the top. So we can just, so this is the equilibrium position of the piston, and it is at a distance of x from the top. Therefore, we can write that new volume V prime will be equal to pi r square times x, and we know that it is a basically isothermal process because it is sealed now, and we can say that our for isothermal process we can write that our PV is equal to P prime V prime, and initial pressure was our P naught, volume we know is our pi r square 2L, and final pressure is our P prime, volume is pi r square times x. So we can say our new pressure, that is our P prime, will be equal to our pi r, sorry, this is pi r square, so pi r square cancels out, so we get this as P prime will be equal to 2L upon x multiplied by P naught. Now we find out once again our equilibrium condition. Equilibrium condition. Upward forces will be equal to downward forces. So from the downward we are still having our atmospheric pressure, that is our P naught, and in the downward we are going to have our mg, and our pressure, a force due to pressure which is inside the chamber. Okay. Therefore we can say that our P naught pi r square, which is atmospheric pressure force in upward direction, will be a P prime pi r square because of the volume or gas inside the chamber, inside the piston and the upper part of the cylinder, and then we are going to have our mg. We substitute our P prime, so this comes as our P naught 2L upon x multiplied by pi r square plus mg, and we can write this as our P naught, and if we divide throughout by pi r square, so this will be coming as our P naught 2L upon x plus mg upon pi r square. P naught terms we can just move to our left, so this comes as P naught 1 minus 2L upon x is equal to mg upon pi r square, and we can further write it as 1 minus 2L upon x is equal to, this will be coming as our mg P naught pi r square. So we can say that our x will be equal to, this will be our 2L 1 minus mg upon pi r square p naught. And okay, we can just take the LCM and move it everything into the numerator. So we get that our x will be equal to, we have this as our pi r square p naught, and this will be also our pi r square p naught minus mg whole multiplied by 2L. So we have our pi numerator is option D is correct. Option D is correct. Next question. Yeah. It was asked in the year 2007, and it states that the piston is taken completely out of the cylinder. The hole at the top is sealed. A water tank is brought below the cylinder and put in the piston so that the water surface in the tank is at the same level as the top of the cylinder as shown in the figure. The density of the water is rho. In the equilibrium, the height h of the water column in the cylinder satisfies. And so in this case, we are having a cylinder which is open at the bottom and the top is being sealed, and later on we seal the hole and the piston is completely removed, and we can say that initially when the cylinder is open it is at the atmospheric pressure. Then we place the, you can say, water and everything. Okay, so let us describe first of all the initial setup. So initially we are having cylinder is open at the bottom, cylinder is open at bottom. Okay. And one second. So we have a cylinder is open at the bottom and has a sealed top. And the piston is completely removed. So cylinder is open to the atmospheric pressure, open to the atmosphere at the bottom, initially. That's why we can see there is no water present here. Okay. Now we place as a water tank. So we can say water tank placement. And this water tank placement, it states that it is positioned such that the water surface of the tank is at the same level as the top of the cylinder. Okay. So we can say that water surface in the tank is at the same level as the top of the cylinder. Top of cylinder. Okay. And we are also given that let us take that the bottom of the cylinder is at z is equal to 0 and top of the cylinder will be then at our z is equal to L naught. Okay. So we can say that bottom of the cylinder let us take at z equal to 0, therefore water level in the tank is at z is equal to L naught. And the third will be our, now the water enters the cylinder. So we can say water enters the cylinder, and because its bottom was open, so water is going to enter the cylinder and that height is said to be given as h. And so therefore we can say this is our z is equal to h. You can see water surface inside the cylinder is at z is equal to h. Okay. And because initially the cylinder was open, so there will be a gas at atmospheric pressure inside the cylinder, but because of the water there will be some, you can say this gas will be a little bit compressed, and we can divide this entire section into two parts. First will be the volume which we occupied by the gas or air at the atmospheric pressure, and second will be our volume occupied with the water of height h. Because we can divide this cylinder into now two parts. When water was not there, the entire thing was occupied only because of the air. Now presence of water we can divide into two parts. First will be our air and second will be our water. So you can say that the cylinder contains air at atmospheric pressure, and atmospheric pressure is about P naught. Therefore, volume V naught will be equal to pi r square times L naught. Okay. And this is our, you have to remember, this is before water enters. Before water enters. And after water enters, volume occupied by water will be equal to pi square h. Let us call this as VW. And from here we can also say that the volume of gas, the gas volume will be equal to, let us call this as our now V gas will be our pi r square, and only the height will be reduced, that is L naught minus h. And so it means our this under equilibrium all the forces will be in balanced, and we know that our cylinder is conducting, and therefore we can say it is an isothermal process. So forces and pressure in the equilibrium. Forces and pressure in equilibrium. So first of all, let's find out the pressure inside the cylinder at the bottom. Pressure inside the cylinder at the bottom, which basically means at Z is equal to 0. And we are only talking about the water which is inside the, we can say pressure which is inside the cylinder. So inside the cylinder we have a water column which is having height of h, okay, and there will be a, you can say, air trapped inside the, so let me draw it here. So we are only talking about this portion. So we are having water whose height is given as h, and we are having this air trapped, and this height is our L0 minus h. Okay. And the pressure inside the cylinder at the bottom. So we can say that pressure at the bottom inside the cylinder will be equal to our pressure P, and we have this as rho GH. Okay. And this we assumed here that this is at a pressure P, and this is nothing but a water column which is height is h. Rho is the density of the water and g is our acceleration due to gravity. Okay. And now we are going to find out this gas pressure P. So we can say our gas pressure P, and we know that initially the gas was occupying the entire cylinder, and this entire cylinder was having a length of our L0, and its volume we know is our V0. We just found out that also. Therefore we can say that our initial volume of the gas, initial volume of the gas, that is our V0, will be equal to pi r square times L0, and this is at pressure P0. At pressure P0, because of the water, this you can say this gas will be compressed, so that's why this pressure is P, which is different from the P0. And we also said that our compressed volume, which we called as Vg, so we can say that when water enters to height h, the gas is compressed to the volume, and we call this as our Vg, and this our Vg will be equal to pi r square L0 minus h. So this is isothermal, that is PV is equal to constant. So we can say isothermal process, which gives us that our PV is equal to constant, and we can write that our P0 V0 is equal to gas pressure is our P and volume is our G. So we can say our P0 V0 is our pi r square L0 is equal to our P, and this comes as pi r L0 minus h, and this pi r square cancels out, so we get our P is equal to P naught and L naught upon L naught minus H. Therefore, we found our value of P, and let be this equation number 1. So we can say from equation 1, we can write that the P bottom inside, we can write this as a P naught, L naught minus H, and plus rho G H. Now we come to the pressure outside the cylinder at the bottom. Pressure outside the cylinder at the bottom. Now in this case, we can just draw our container, and we have this water. So this is a cylinder, and this cylinder was having a water up till this, but outside the cylinder the water is up to the height of L naught, and we are going to have atmospheric pressure also. Okay, from the inside we found out, and now we are going to find out the outside part. Therefore, we can say that our P bottom outside will be equal to our atmospheric pressure and total, you can say, the column water pressure, which is our rho G L naught. And under equilibrium condition, we can say the pressure inside should be equal to our pressure outside. So we can say our equilibrium condition we can write that our P bottom inside should be equal to P bottom outside. So we simply substitute them. We get this as P naught L naught minus H plus rho G H will be equal to P naught plus rho G L naught. And we can just simplify it. We get this as our PL naught plus we have rho G H L naught minus H minus P naught L naught minus H minus, and this is our rho G L naught, and L naught minus H is equal to 0. And we simply open everything. So we get this as P naught L naught plus rho G H L naught minus rho G h square minus p naught L naught plus p naught h, and this comes as minus rho g L naught square plus rho g L naught h is equal to 0. And this p naught L naught p naught L naught cancels out, and this is our rho g h L naught, and this is also rho g L naught h. So we can add them. Therefore we get this as our 2 rho g h L naught, and rest we can write as it is, minus rho g h square plus p naught h minus rho g L naught square is equal to 0. And we can just rearrange it, and that is going to give us answer directly. Or we can write this as our rho g we can take as common, so we have this as rho g, and let us take as minus rho g, so we are left with our h square minus 2h L naught plus L naught square, and this will be our minus p naught h 0, or we can take minus throughout, so this will be coming as plus. So we can say this will be our rho g, and we have this as h minus L naught whole square, and sorry, 1 second, this is reverse, it is plus here, so it will be plus if we take minus common throughout, so this will be coming as minus, so this will be minus p naught h is equal to 0. And in order to match our answer, we can write this will be equal to our rho g, and we have this as our L naught minus h whole square, this comes as p naught, and we have L naught minus h minus p naught, and L naught is equal to 0. So our L naught minus h, and we have our p naught plus minus, option C is correct. C is correct. Next question. It was asked in the year 2009, and it states that a metal rod AB of length 10x has one end A in the ice 0 degree centigrade and other end B in water 100 degree centigrade. If a point P on the rod is maintained at a 400 degree centigrade, then it is found that equal amounts of the water and ice evaporates and melt per unit time. The latent heat of evaporation of water is 540 calorie per gram, and latent heat of melting of ice is 80 calorie per gram. If the point P is at a distance of lambda x from the ice end A, find the lambda. Neglect any heat lost to the surrounding. Okay. So we can just draw the basic figure for that. So we have a rod AB, and A is at 0 degree centigrade and at B is at 100 degree centigrade, and in between we have a point P. Suppose this is our point P, and this point P is at a distance of lambda x, and total length is given to us our 10x. Therefore, from end B, this will be our 10 minus lambda, and x we can take as common. And the temperature at point P is said to be at 400 degree centigrade. Okay. And it is also said that equal amounts of water as well as ice evaporates and melt per unit time. So first of all, we have two segments here, AP and PB. Okay. A is at 0 degree centigrade and P is at 400 degree centigrade. Okay. And PB is our other segment. Temperature is from okay. So we can say that P is at a higher temperature than A, so heat is going to flow from P to A. Okay. So we can say that heat flows from P to A. Okay. And because of this heat flow, ice melts. And there will be our heat flow from also from our P to B, and because of this the water evaporates and ice melts at 0 degree centigrade, and we have our water evaporates at 100 degree centigrade. Okay, and it is said that equal amount of water evaporates as well as ice melts. So we can use our conduction formula, which is called as a heat conduction formula, and it is also called as a Fourier's law. So we are having our heat conduction, which is also called as our Fourier law, and it gives us that our Q is equal to Ka delta T divided by L. Q is the heat flow rate, K is the thermal conductivity, A cross-sectional area, delta T temperature difference, and L is the length. And because this rod is same, therefore our K and A will be same for entire section, PA section as well as our PB section. So let us first of all discuss our PA section. So we can say that our segment PA, and the segment PA length is lambda x, and its temperature difference, that is delta PA, will be our 400 minus 0, giving us 400 degrees centigrade. Therefore we can say that our heat flow, that is our QPA will be equal to, we get this as Ka multiplied by 400, and length is our lambda x. And now we know that this amount of heat is going to melt the ice at 0 degree centigrade. You can say this heat melts ice at 0 degree centigrade. Therefore, we can write that QPA, that heat required to melt the ice. Heat required to melt the ice, and ice of mass m, and that will be also our QPA will be equal to our mass m and latent heat of fusion, okay, which is given to us as 80. So this comes as mass multiplied by 80, and these two terms are our same because heat given will be heat taken by the ice. Okay. Therefore, we can say this will be equal to our 400 Ka divided by lambda times x. So from here we can write our mass m will be equal to, this will be coming as 0 and 0, and we have our this goes by 5, so we get this as 5 Ka upon lambda x. Lambda x, yeah, lambda x. Okay. Now we come to the other part, that is our PB, segment PB. Segment PB, which is of the length 10 minus lambda times x, and the temperature difference TPB will be equal to 400 minus 100, giving us 300 degree centigrade. Therefore, we can say our heat flow, that QPB will be equal to our Ka, and the temperature difference is our 300, and length is our 10 minus lambda times x. Now this heat is used to evaporation. So we can say this heat evaporates water at 100 degree centigrade. Therefore, heat required to evaporate mass m prime of water, that will be also our QPB, and that will be our m prime latent heat of evaporation. And that is our m prime given as 540, and that will be equal to our 300 Ka 10 minus lambda upon x. From here we can find out our m prime. M prime will be equal to, this comes as our 5 Ka 9 10 minus lambda times x, but it says that the mass evaporated per unit time for water and ice melted per unit time, which is our m, is same. So we can say that our m is equal to m prime. Therefore we can write this as 5 Ka lambda x is equal to 5 Ka 9 10 minus lambda times x, and this is 5K x and x cancels out, so we get this as our 90 minus 9 lambda is equal to lambda. We get lambda is equal to 9, which we are supposed to find out. Next question. It states that it was also asked in the year 2009, and it states that C of V and C of P denote molar specific heat of gas at constant volume and constant pressure respectively. Then we have to find out the various combination of their subtraction, addition, division and multiplication, okay, for diatomic, and make a comparison between diatomic and monatomic. Okay, and these are quite standard relationship, so we can just write them directly, that our C of V is equal to F upon 2 times R, okay, where F is the degree of freedom. And we also know that our C of P is equal to C of V plus R. Okay, so we have two types of gases, monatomic and diatomic. So first of all, let us monatomic. For monatomic gas, we have our degree of freedom, that value of F is equal to 3. Okay. Therefore, we can write that our C of V for our monatomic will be equal to 3 by 2 times R, and we can say that our C of P for our monatomic will be equal to 5 by 2 times R. And next is our diatomic. And for diatomic, the degree of freedom is above 5. Therefore, we can write that C of V for our diatomic will be our 5 by 2 times R, and C of P for our diatomic will be equal to 7 by 2 times R. Now we can just find out or troubleshoot what are the options given to us. So we have our option A. Option A, we are supposed to find out Cp minus C of V. Okay. So let us do it for monatomic. So we can say our Cp mono minus Cv C of V mono, and this comes as 5 by 2 minus 3 by 2, which comes as our R. Now let us consider it for C of P as dia, and C of V is also our dia, and this comes as our 7 by 2 R minus 5 by 2 R, and this also comes as R. Okay. So both are equal. So therefore option A is incorrect. Now we come to their addition. Option B, C of V plus C of V. So let us do it for our mono. And we get this as our 5/2 of R plus 3/2 of R, which comes as our 8, and we can write this as a 4 times R. And now we come to our dia. C of V for our dia, and this is our 7/2 plus 5/2, and this comes as our 6 of R. Therefore, we can say that for diatomic it is greater than. So option B is correct. Now we come to option C. Option C is the ratio, that is our C of P and C of V. So we can write this as our C of P of mono, C of V of mono. This will be equal to our 5/2 and 3/2. This gives us 5/3, approximately 1.667. And then we come our C of P of dia, and C of V also is our dia, and this comes as our 7R/2 and 5R/2, which is our 7.5 is equal to 1.4. Therefore we can say that this mono is greater. Okay, and so this option is also incorrect because it says dia is greater. Now we come to the option D. We have their product C of P and C of V. So C of P for our mono dot C of V of our mono, which will be equal to 5/2 R, and we have this as 3/2 times R, giving us 15 4R square. And then we come over C of P of dia multiply by C of V of our dia, which comes as our 7 of 2R and 5 of 2R, which gives us 35/4 times R square. So this portion is greater than. Okay, and therefore option D is also correct. Is correct. Next question. It was asked in the year 2009, and it states that the figure shows a PV plot of an ideal gas taken through a cycle ABCD. The part ABC is a semicircle and part CDA is a half of an ellipse. Then we have to find out, or we have to check, what are the various processes. Okay. So we are given that our ABC is a semicircle. So we have our A, B and C is a semicircle. Okay. So we start from there only. We are given that our ABC is semicircle. From here we can write our coordinate of A, and we are given that our coordinate of A is 3, 2. Our B is our 2, 3. One second. Okay, anyways, it doesn't matter how we write the coordinates, because okay, and we have our B, that is our 2, 3, and we are having C, which is 1, 2, and this we have written as per our PV plot. Okay, we have to remember this is with respect to a PV, okay, not as per XY. Okay. And the other cycle is our CDA, which is, you can say, part of ellipse. Sorry, it is also half of ellipse, not part. Half of ellipse. And for that we can once again write the coordinate. C is our 1, 2, and we have our D. D is our 2, 1, and we are having our B, not B but A. A is our 3, 2. So if we see the entire cycle, it starts from A and ends at A. Therefore, the net change in internal energy will be equal to 0. So we can say that cycle is closed because it starts from A, B, C, D and back to A. Therefore, from here we can say that net change in internal energy delta U will be equal to 0. Okay. And then we are going to use various our processes. Okay. And so let's find out what will be the, for our ABC, how the pressure and volume is going to change. So first path is our ABC, and in the first path it starts from A, that is our 3, 2, and it moves to B, which is our 2, 3. Remember, this is our pressure, volume, pressure, volume. So obviously we can say that the pressure is decreasing and volume is increasing. So we can say our pressure decreases and our volume increases. Okay. Now we come over from B to C. Our B is 2, 3 and our C is 1, 2. So once again this is pressure, volume, pressure, volume. So the pressure here decreases and volume also decreases. So you can say that our pressure decreases and we have a volume also decreases. Okay. And now we come over for our path, that is our CDA. Path CDA, and so for C, it starts from C and the coordinate of C are 1, 2 and it goes to D and the coordinate of D are 2, 1. So we have pressure, volume, pressure, volume. Okay. So here our pressure increases and our volume decreases. Now we come to our back D to A. So our D is our 2, 1 and our A is our 3, 2. So we have a pressure, volume, pressure, volume. So here the pressure increases and volume also increases. Okay. And so let's evaluate. First option, that the path AB is isothermal. From A to B is our isothermal. So we have option A. And it says that our path AB should be isothermal. Now if we assume that this is isothermal, then we know that for isothermal process we are having that our PV is equal to constant, and from A to B we know this is our 3, 2 and B is our 2, 3. Therefore we can write our PA VA is equal to PB VB. So we can write this as our 3 multiplied by 2 is equal to 2 multiplied by 3, which gives us 6 is equal to 6. So this could be isothermal, but we have to also check by using the, you can say, semicircular option also. Okay. So we can say that A to B could be isothermal, could be isothermal. Okay. Therefore, let us consider our semicircle. So we can say for semicircle, we can write the equation that P minus 2 whole square plus V minus 2 whole square is equal to 1. And I think this and so let us write that our parametric form. So we can say in parametric form our P will be equal to 2 plus cos of theta and V will be equal to 2 plus sine of theta. Okay, this is parametric form of the equation, and we are having the path, one second, ABC. Okay, so it means at A our volume will be equal to 2, giving us sine of theta will be equal to 0, or we can say our theta is equal to 0. Okay. And our pressure P will be equal to 2 plus cos of 0, which is 2 plus 1 is equal to 3. And at B we are having that our pressure is equal to 2 and our cos of theta will be equal to 0, which tells us our theta is equal to pi by 2. And for here we can write our volume will be equal to 2 plus sine of pi by 2, which comes as 2 plus 1 is equal to 3. And at C we can say our volume is equal to 2 and our sine of theta is equal to 0. Therefore we can say our theta is equal to pi. Therefore our pressure P will be equal to 2 plus cos of pi, which gives us 2 minus 1 is equal to 1. So let us check our product of PV. Pressure volume product will be equal to 2 plus cos of theta, and we have this as 2 plus sine of theta, and we simply expand them. We get this as our 4 plus 2 sine of theta plus 2 cos of theta plus sine theta cos theta. Okay. And in this case we know that our, at least at 2 points which we just calculated here also, let me, okay, for these two values, these two values we calculated at theta is equal to 0 and theta is equal to pi by 2. But for intermediate value we are not very sure whether this relation is going to hold or not. So we can say that same thing I'm going to write but in the form of theta. So we can say our theta is equal to 0, therefore our PV is our 3, 2, which comes as a 6, and if theta is equal to pi by 2, we get our PV is equal to 2, 3, which is also over 6. Okay. So these are only at the extreme point, but at the intermediate point, let us consider theta is equal to pi by 4. So we can say for intermediate point, that is our theta is equal to pi by 4, and we can say that our P will be equal to 2 plus cos pi by 4, which will be coming as our 2 plus square root of 1 by 2, and we have our volume V, which will be equal to 2 plus sine pi by 4 will be equal to our 2 plus 1 by square root of 2. Now if we find out their product, that will be equal to 2 plus square root of 2 whole square, which will be approximately equal to 7.3, obviously not equal to 6. And 1 second. Okay, sorry. I took this intermediate point somewhere here, so let us call this as intermediate point as our X. Okay, not as C. For intermediate point as X. Okay. So obviously this is not consistent with our PV is equal to constant. Therefore we can say that our PV is not constant along A to B. Therefore not isothermal. Okay, from the start of this it looks like it might be isothermal, but it is not a isothermal process. Now it says that heat flows out of the gas during the process BCD. Okay. That is our option B. Let's start with our option B, and from our first law of thermodynamics, we know that our delta U is equal to Q minus W. Okay. So when heat is added, or we can say we have to find out the heat flows out of the gas, so this Q must be negative. So we can say that our heat flows out if our Q is less than 0. So let's calculate our internal energy. Internal energy, we know that our delta of U is equal to NC of V, and we have this is delta T. And so let us calculate our temperature. So we can use our equation, that is PV is equal to nRT. So we have our temperature T will be equal to PV N times R. So we have 3 points, that is our B, C and D. So let us do it for at B. We can write this as a PV VB will be equal to 2 multiplied by 3, which is about 6. Therefore, we get a temperature at B will be equal to 6 upon nR. And then we have our D is equal to PD and VD will be equal to 2 multiplied 1, which is about 2. So temperature at D will be equal to 2 upon nR. So the temperature difference, that is delta T. So we can say our delta T for our BD process will be equal to temperature at D minus temperature at B. So we get 2 times nR minus 6 times nR, giving us minus 4 times nR. Therefore, we can say that our delta U for our BD will be equal to, we have N C of V minus 4, and this is our N times R, and N cancels out, so we get this minus 4 C of V upon R. And so we have our delta U is our negative, therefore we can say, okay, from here we can say that our, which is less than 0. So let's find out the work done. So we can say our work done for the path BC will be equal to integration B to C and P dV. Okay. And for path B to C, we have already written that our for path B to C, there is a decrease in pressure as well as the decrease in volume. So it means this our dV will be negative. We can say that our V decreases, therefore we can say our dV will be less than 0. So which basically means that the work done will be less than 0, that is negative. And let us verify by using the parametric form of our equation. That is going to confirm whether this is true or not. So we are going to parameterize the semicircle. Semicircle, we know that our P is equal to 2 plus cos of theta, and we are having V is about 2 plus sine of theta, and here theta is going to vary from pi by 2 to pi. So we get our work done, WBC is equal to pi by 2 to pi, and this comes as 2 plus cos of theta and this derivative of 2 plus sine of theta, and we can just put the values. So let me write the answer directly because it is quite simple to solve. This will be coming as minus 1.215, which is less than 0. So we have our work done is 0, and so work done is 0, Q was also 0. Therefore we can say that our, let me write the equation, and that equation was our QBD is our delta U BD plus W times BD. Okay. And we know that our this delta U BD is less than 0, and this WBD is also less than 0. Yeah. Therefore, we can say that our QBD will be also less than 0. So heat flows outward. Therefore, we can say option B is true. Option B is true. Now we come to the option C. Work done in the path A, B, C is 0. So work done in the path A, B, C will be equal to work done from the path A to B, then plus B to C. Option C. So work done in the path A, B, C will be equal to work done for the path AB plus work done for the path BC. Okay. And once again we are going to use our pressure is equal to 2 plus cos of theta, and volume is 2 plus sine of theta. Theta is going to vary from 0 to pi by 2. So, and this is for AB, A to B, and we can write that our work done AB will be equal to 0 to pi by 2, 2 plus cos of theta, and derivative of this will be also coming as cos of theta and d of theta, and this comes approximately equal to 2.785. And we already know that our work done for BC is approximately minus 1.215. Therefore, net work done ABC is equal to 2.785 minus 1.215, which is approximately equal to 1.57, which is not equal to 0. So option C is false. Is false. Now we come to our option D. So option C is our false. Option D is positive work is done by the gas in the entire cycle A, B, C, D, A. Okay, and for that we can use our approximately we can find out with respect to our areas. So we have our option D. So positive means it should be greater than equal to 0. Okay. And let's find out the approximate areas. So we have a semicircle, and semicircle is our pi r square upon 2, and a radius is over 1, so this comes as pi upon 2, which is approximately equal to 1.57. And okay, here I think we are only interested in the sign, so there is no need to calculate, because if you want to do it for our ellipse, no doubt we can calculate the area, but that will be requiring a lot of integration work. Okay, so we are only interested in sign, so we can say that our semicircle area, let me write it, work done for our semicircle, which is for work done our ABC, is greater than 0. Okay, and we have our ellipse, area, which is our work done, our CDA will be also greater than 0. And we know that our, for the closed cycle, we have delta U is equal to 0. Therefore our Q net will be equal to our W net, and which is greater than 0, or we can say positive. Therefore option D is true, So option D is true. So only B and D are correct. And I think this was the last question. Yeah. So this completes all the questions. I think we did 9 questions, if I'm not wrong.